Hello everyone, my name is Sadullah and I'm a third year PhD candidate at Boston University. And today I will be presenting our work on evaluating large language models for their capabilities of identifying and reasoning about security vulnerabilities. So with the advent of large language models and their capabilities as general purpose assistants, they have become the basis of a lot of automated tools, especially in cybersecurity, where they have been unleashed in automating tasks like vulnerability analysis, vulnerability repair, or also automated software test generation. So far, their evaluations have been focused on insecure code generation or vulnerability repair. However, for vulnerability detection, the evaluations were either focused on small large language models and focusing just on binary classification capabilities, which leaves the evaluation of their root cause analysis capabilities completely unexplored. And without this question remains still unanswered. That can these large language models be used as helpful security assistants and help us in vulnerability detection? To answer that, we developed SecLLM Homes, which is a fully automated end-to-end framework for benchmarking and evaluating large language models for vulnerability detection. And as compared to the previous studies and evaluations, not only it performs an evaluation over more diverse dimensions, but also does it in a completely automated way. Moreover, it introduces a novel, fully automated approach to evaluate the reasoning or root cause analysis capabilities of large language models. So our framework consists of three modules. First is the prompt creation module, which designs those testing prompts, which are then passed to the LLM that you configure, and the responses are then fed to the evaluator. Starting with the LLM configuration. So if you want to benchmark or evaluate any LLM, we design a simple three-step process that you can follow to configure any large language model, starting with defining the prompting strategies, because every model is instruction tuned in a different way, and different models provide different documentation on how can you get the best results by using a specific type of prompting. For example, OpenAI asks us to surround the text in 3 quotation marks. However, Google tells us to use those semantic keywords in front of the content. And you can define these three functionalities, defining the prompt strategies, initializing the model, and integrating the chat inference API or inference code. And you can do all of that in just 30 lines of code, as shown here, an example of the GPT-based adapter that we built to configure GPT-based models. So after this, you just have to press run, and the rest is taken care of by our LLM. By our framework, and where our prompt creation module uses our benchmark dataset, which is made up of handcrafted scenarios, augmented and real-world CVE scenarios with 3 different code complexity levels, making sure that all of these scenarios are outside the knowledge cutoff date of large language models. And then it combines them with an extensive set of prompt templates over 3 categories, with standard prompts, which ask the question directly, or step-by-step reasoning-based prompts, and moreover, providing in some prompts the definitions of vulnerabilities. And combining these, it performs evaluations over these 8 dimensions, starting from looking at the best parameters for getting the best results, and what are the best prompts for this task to get the best results. And after setting these best parameters and prompts, it runs these stress tests to test the capabilities of LLMs over a dimension, over a variety of different code scenarios and difficulty levels. So after these prompts have passed to the LLM, they are fed to the evaluator. And how our evaluator works is we will look at an example. So let's say this is a code scenario that encodes a certain character in the given user input, but this code assumes that the encoding expansion of every character will only expand by a factor of 4. However, the ampersand encoding expands by 5. So if an attacker provides a string of many ampersands, the string will overflow the destination buffer. And this is a classic example of out-of-bound write. So when you ask different models based on different prompting, you will get different types of responses, but all of these responses would have 2 things in common. First is the answer, what is this vulnerable or not? And the second would be the reasoning behind it, why this is vulnerable, which is the root cause. So our goal is to evaluate these two things. So how we do it, these responses are fed to our evaluator, where our evaluator leverages GPT-4 to extract these two specific fields from these responses. And the answer, yes or no, is compared against its own ground truth to evaluate the accuracy. However, the reasoning extracted by GPT-4 is compared against the ground truth reasoning designed by three security experts, and it is compared using NLP metrics to see if they both align with each other or not. So that's how we find out if the final answer and the reasoning is correct or not. So after designing this framework, we ran an evaluation study on these 8 most capable LLMs at the time of publication. So starting by looking at what are the best parameters for this task for these large language models, we found out that we got the most accurate and deterministic responses for vulnerability detection at temperature 0 and top P1. And when a higher value of temperatures led to more inaccurate reasoning as well as inaccurate answers. On the other hand, we observed the most non-deterministic behavior by GPT-4 even at temperature 0, where when we asked the same question again and again, not only it kept changing its reasoning, but also kept changing its answer from yes to no. So after setting these best parameters, we ran extensive study on test by using our framework on identifying the best prompts. And we found out there's not an overall best prompt that works best for each LLM. For example, the smaller models perform better when provided the definitions of vulnerabilities. However, there were some models which were already good at giving you answer when asked the question directly. However, for the GPT-based model and the code-tuned Chat Bison model, we were able to get best accuracy by using a step-by-step reasoning, which is completely different than just asking a model to think step by step. However, we provided them instructions based on the previous literature on how human security experts do vulnerability analysis. And when we asked them to mimic the same process, and we will look at an example of this code, which has a null pointer dereference, because when opening a file, it does not see if the file exists, or it returns a null pointer and it just starts reading the file. And this can cause a null pointer dereference. And when we asked the large language model to mimic the process from this study, and when we provided those instructions, not only it identified the right vulnerability, but also provided us the right reasoning that fopen function can return null and the code does not check it. And we found out that only by using this, we were able to get good reasoning, and the other prompts and even other step-by-step prompts did not provide us the right reasoning, and which showed us that the LLM's reasoning for security vulnerabilities is not consistent with the practices that are followed in the real world by security experts. Moreover, we found out that even with the best prompts, you can get unfaithful reasoning, which means you can get the right answer and the reasoning could be wrong. However, in another case, let's take an example of a code which is validating a given command to check for command injection, but here it only checks for a semicolon. However, if you want to concatenate command, you can also use other characters. When we asked the model, it did the reasoning correctly. That yes, you can use the $sign, the pipe sign, or the ampersand sign to concatenate the command, and your code does not check that. But still, somehow, at the end, when giving the final decision, the model said that your code is safe. So this shows another example of unfaithful reasoning. And lastly, after setting these best parameters and the best prompts, we ran the test to test different capabilities of LLMs, starting by looking at variety of vulnerabilities, where we found out that not every LLM has a knowledge about all the vulnerabilities, and most of them are biased towards out-of-bound right. This also helped us get insights about the different models. For example, we found out that Code Chat Bison does not respond to out-of-bound right and use after free vulnerabilities, especially in few shot scenarios. which are among the top three most dangerous software weaknesses in the list of 2023. On the other hand, when tested over different code difficulty levels, we found out that LLMs find it really difficult to deal with codes that are lengthy, as well as they have different and complex functional densities. Similarly, in the case of real world cases, we've observed a really high false positive rate. And interestingly, we found more doubtful answers like, I'm sorry, I'm not able to help with that because I'm only a large language model. So our last dimension was robustness, in which we designed different code augmentations, and we were able to break the chain of thought and step-by-step reasoning of large language models using our test cases from ranging from 17% to 30% of our test cases. So starting from a very trivial augmentation, this is the code that I showed before about which is encoding certain characters, and it has an out-of-bound write vulnerability. So whenever we saw it, you give this code to ChatBison, it will always say it's vulnerable. But if you add a certain number of spaces after line 22, it will always say that the code is safe. Moreover, we looked into some trivial and non-trivial code augmentations in which we provided the names, for example, strcat in terms of out-of-bound write or escape function call in terms of cross-site scripting. And we found out that the models focused just on those functions as they were biased towards those and made the wrong choice and gave us the wrong answer. So in conclusion, we developed SecLLM Homes, which is an end-to-end evaluation framework that you can use to benchmark LLMs. And our evaluation study highlighted various strengths and weaknesses, especially in reasoning of large language models. And for the limitations, as you know, our evaluator is dependent on GPT-4 to extract the final answer and the reasonings. And because of some edge cases that GPT-4 was not able to handle, there were some inaccuracies in calculating the reasoning and evaluating the reasoning. Moreover, if you want to test the latest LLMs, which for that you might need to select those CVEs by yourself that are outside the knowledge cutoff date of that large language model, and so that you can maintain the temporal consistency of the evaluation. But for future directions, I would encourage you to use our framework to benchmark new LLMs and highlight their breakpoints. You can design your own code scenarios, own code augmentations, and run these experiments to highlight different breakpoints and pitfalls of these LLMs. Not only that, you can also use our framework to build better large language models for cybersecurity and use these insights from our study or the studies that you perform. We open source our framework and dataset under the AI for Cloud Up organization. And if you have any question, please reach out to me through this email.